All right, we're back. We're on page 117 of math analysis. This is actually the first page of notes 11. And what we're going to be doing is we're going to be talking about two-dimensional vectors. And two-dimensional vectors are really cool. Vectors in general, I think, are really cool. So I guess when I think about math analysis in general, one of the things that I think of is the unit circle, for sure. It permeates everything. We talk about it all the time. It helps us solve a lot of problems, just kind of constantly are referencing back to it. Another thing I think is we're going to talk about ways that you can just represent points in the plane, and they have different advantages and disadvantages. So for example, if I just give you the point A and the point B, and I said like add those together, it doesn't really make any sense. What does it mean to add 2 points? It doesn't mean much of anything. We want to figure out ways that we can talk about maybe multiplying a point by something. Like, what does that mean? Adding them together, subtracting them, things like that. So one of the ways we're going to kind of introduce that idea is to talk about vectors. You may know something about vectors because they're sort of in geometry. In geometry, I feel like the way you run into vectors is like someone tells you to move like 5 units east and then 3 units north. And then the question is like, what's your relationship to where you started, right? So that's a very vectory concept. You might be in physics or have already taken physics or studied for an SAT of some sort or whatever. Where you would have run into vectors as well. If you don't know anything about them, that's also okay, because that's what we're going to kind of assume here. So vectors are quantities. And what's a quantity? Well, it's just like a mathematical object, I guess, that have both a magnitude and a direction. So a lot of things you're used to have a magnitude. So for example, things with magnitudes, like the length of something, the volume of something, like 8 cubic inches. You don't say like 8 cubic inches up or 8 cubic inches down. You just say it has a volume of 8 cubic inches. Temperatures, right? So it's 32 degrees or 57 degrees. Like that's it. That's all you get there. And then speed. Now speed is interesting. You say like 5 miles per hour. So speed, I think, is a really good connection between what are called scalars, which are quantities that only have a magnitude, and vectors, which have magnitude and direction. Because speed is useful. Like say you were going to watch a race, right? And you happen to know how fast, it's a race between 2 people, and you know how fast both of them are gonna run, right? You know their speed. So here's the start, and let's say here's the end, right? Okay, so you know the speed at which everyone's going to go. You know that person A, let's say, you got A and you have B. Let's say you know A is going to go 7 miles per hour. So 7 miles per hour. And let's say B, you know, is going to go 5 miles per hour. And if someone said, you know, who are you going to bet on? Well, you're obviously going to bet on A based on what you know, because A is going to go 7 miles per hour, B is going to go 5 miles per hour. There's no way that B is winning this race. That's based on their speed. But what if you knew the vector that they were going to go? So you knew the magnitude, which is 5 miles per hour, 7 miles per hour, and the direction, right? So what if you knew that A was going to go 7 miles per hour, but in this direction, whereas B is going to go 5 miles per hour, but in this direction? Now you're betting on B. So this is where vectors come in handy, because they give you a magnitude, the 5 or the 7, and the direction. It's just more information. So let's see what they mean for us initially. So initially, we're going to talk about the geometric representation. And it really just looks like a line segment with an arrow pointing in the direction that you're going. So for example, if I were going to create the vector AB, so the notation looks a lot like the notation for a ray from geometry. So this is our notation, right? So it's the vector from A. So you start at A and you end at B. So when you draw it, it's just going to look like, maybe I'll use a different color here. It's just going to look like that. So sometimes when you draw your vectors, you have to put an arrow pointing in the direction it goes, right? And then you have to go from A to B. It has to have the correct length. So I'm going to put this back, but this vector from A to B is actually the same as like this vector, because it has the exact same magnitude. It's still the same length, and it points in exactly the same direction. And I can take it and move it basically wherever. These are all the same vector. There's only one vector that conveys that information. The information is move in such a way that you start at point A and end up at point B. But it's just information. And you might look at the information and you might kind of say to yourself, well, this information is move 3 units to the left and then move 3 units down. That's one way of thinking about it. So that's the vector from A to B. We also need the vector from C to D. So C to D, I will use this color. And so we are going from C, so we're going to start at C, and then end at D. Now, if you have a lot of vectors that are pointing at the same thing, so for example, you might have a lot of vectors that are ending at D. It can get confusing and jumbled because they all have these arrowheads there. So what we'll do instead, I gotta erase those. What we'll do instead sometimes, not always, but it's convenient, is to put the arrow in the middle. So you'll see that sometimes, not always, but sometimes. So I think it's more common to see it kind of at the end, but this conveys the information, right? Now, if you look at these two vectors, you will notice, I think, that, here, let me just do it. They have the exact same length, but they're not the same vector. They're not the same vector because they're pointed in exactly opposite directions. So they have the same length, but different directions. Direction is going to be harder for us to figure out. Magnitude is not going to be that bad. In fact, you probably already can figure out how to figure out the magnitude of these vectors. But let's see if we can just convey the information, right? So what is vector AB? So that's how you would say it, vector AB, which is a vector that starts, it has its initial point. Here, let me label that up. So this is an initial point at A. This is its terminal point. So you have an initial point and a terminal point. And when you name it, you go from initial to terminal. It's the vector AB. And you put a little arrow on top, and you're good to go. So for CD, the initial point is C, the terminal point is D, and that's it. So what is AB conveying? For me, AV is conveying the following information. You always talk about left, right first, and then you talk about up, down. It's saying move 3 units left, and then move 3 units down. So I'm going to say that the vector AB is telling you to move 3 units left and 3 units down. So for example, if you started at 1, 1, say you start at the point 1, 1, which maybe I shouldn't do. Wait, let's say we started at the point 2, 2. And then someone said, you know what, from 2, 2, apply the vector AB. Apply that set of directions. Well, what are you going to do? You're going to go 3 units to the left. You're going to go 3 units down. And you will end up doing this. So it's just a set of directions, but it's a set of directions that takes you from a starting point to a terminal point and tells you what to do. So the vector AB says move 3 units to the left, move 3 units down. Where are you going to start? Wherever you want. As soon as you choose a starting point, you have to move 3 units to the left, 3 units down. That's how the vector works. The vector CD is kind of the exact opposite. So CD, you can see, is telling us to go 3 units right and then 3 units up. So you always go left, right first. 3 units right, 3 units up. Okay, so no matter where you start, if someone says, you know, it's like everybody's just walking around the room and then it's like pause and everyone stops where they are. And then someone says, now everybody move the vector CD. Everybody's going to move 3 units to the right and 3 units up, which would probably be forward. So that's a little bit of what we're dealing with. Now we want to talk about the magnitude of a vector. So the magnitude is the length. These are similar words, basically the same word. Magnitude equals length, also equals the norm of a vector. And you can see how you would calculate it, right? How would you find the length of this vector? I mean, I'm kind of highlighting it. How would you find the length of this vector? It's basically the Pythagorean theorem, right? So if you look at it, here is what we will say. So the length or the magnitude or the norm, these are all the same. They all mean the same thing. They're not the same word, obviously. So let me just write the length equals magnitude equals the norm. I think of those words, the norm is the weirdest one. However, it's the one that's built into your calculator. So that's kind of strange also. So if you look at it, it's literally, this is really just the Pythagorean theorem or the distance formula. So we're just doing the change in x squared plus the change in y squared and then square rooting it. The notation is weird though. The notation is, it looks like a double absolute value, I guess. So when you draw it, you actually draw that. You're gonna go this, this, and then when you hand draw or name a vector, sometimes you name it with a single letter, it's just more convenient. You have to put an arrow over it. When you type it, you can make it bold. So you'll see both of those, and that's like a little confusing initially. So this is how we're gonna do it. Another way of thinking about it, I think, this way, I think it's a good way to think about it. It's really just delta x squared plus delta y squared and then square root, right? You have a change in x, a change in y, and then square root. If we go up here, we'll just find this one. So for the vector AB, right? So delta x is -3 because you go 3 to the left. Delta y is -3 because you go 3 units down. And so the norm, the magnitude or the length of AB is going to be the square root of -3 squared plus -3 squared, which is 3 root 2. I'm just writing it in a really bad place, but that's what I'm doing. And then if we did it for this one, and then I will stop the video here, this, your delta x is 3, your delta y is 3. So the norm or the length or the magnitude of CD is going to be also 3 root 2. So they have exactly the same length. They're in exactly opposite directions. So this is kind of a little intro. I'm going to come back in the next video, probably use a calculator for some stuff, and maybe also show you a little thing on GeoGebra. I don't really know if that's going to be useful or not. Anyway, we cut the video here. I'll be back in the next one to do some more. So see you there.